Hello everyone, once again to System Verilog Module 4 Part 2. We'll be discussing here the concurrency, synchronization and communication mechanisms in System Verilog. So that's the Module 4 Part 2 and Part 1 comprised of randomization in System Verilog. So to understand what are these three mechanisms, let's understand one by one. So we'll start with threads. So what are threads in System Verilog? In System Verilog, a thread is a sequence of statements that execute concurrently, meaning in parallel, with other threads. Threads are commonly created using constructs like fork join, enabling simulation of parallel behavior, just like in real hardware. So why do we need threads? To model parallel hardware operations, we need them. To run stimulus and monitor tasks in test benches simultaneously, to simulate real-time delays, responses, or timeouts, and to wait for multiple conditions independently. So thread creation is hence the syntax for that is fork followed with join. We have different variants here. The first one is fork join, or the other one is fork followed with join underscore none, or the third variant is fork followed with join underscore any. And we also have disable label, disable fork, and wait fork as the other three variants in threads. Let's see each of them with example. For example, here I have written a module by name test, and inside there is a process inside initial begin. So it's fork and join, and in between I have the two statements, wherein one statement starts after hash 5, 5-time scale. That is displays thread 1 at %t $time. So that gets displayed. And after a delay of 10, hash 10, another display message is written, right? And then it's followed with join. And after this fork join block, we have the next statements of that process, which is $display, wherein all threads complete is the display, which will be displayed at $time. So at that time, the statement in this will be displayed. Now, what happens here? So I have fork join, that's the parallel block written. So when I have fork join mentioned in my program, then concurrent execution happens here, and all the statements execute inside the fork join, and then only then the statements after the block gets executed. So after the block, the statement what we have here is $display. So first, whatever is inside fork join, that gets executed. So first one will be thread 1 at $5, right? So at $5 it gets executed. So that gets displayed with the $display command. Then we have one more $display wherein thread 2, and this is after 10. So it's concurrent, right? So this will happen at 5 and this will happen at 10 because they execute concurrently inside the fork join. So thread 2 executes at 10. Only after the fork join block is completed, then the statement next to the block, outside the block, gets executed. So that is this statement will get executed. So that will happen at 10 because this was the end of the block. The time when the block ended is 10. So this immediately displays, immediately executes, which is the $display command. So all threads complete at 10, right? So this is executed at 5, this is executed at 10. So this finishes at 10. So immediately this statement executes, which will also be 10 hence. So these are the outputs which get executed. Okay, so that's about concurrency using fork join. Now, one more example here I have shown wherein I have used the module by name test and a process here which is initial begin end. So this is a block, and inside the process we have a fork join, right? And before fork starts its execution, we have hash 10 delay. So after hash 10 delay, the fork join block executes. So what happens here? First, the entire block executes after a delay of 10, and only then anything outside the fork join block gets executed. Okay, so at 10, till 10, nothing gets executed here. It's in the process of initial, and then fork starts concurrently executing. So at 20, thread 1. So we have at 10, thread starts. So after hash 10, then we have at 20 plus 10. So this gets added with 20. So at 30, thread 1 ends, right? And then the next one happens at 30 because the earliest one in the concurrency. So 20, 30, and then 40. So 20, thread 1 executes, then 10 plus 20 gets added up, and 30, thread 1 executes. Then 30 plus 10, 40, thread 3 executes. And 40 plus 10, 50, thread 2 executes, right? So this is how the process happens. Then um, the statement outside the fork join, which is $display, gets executed. So what was the last uh, uh, statement which got executed? 40 plus 10, 50, right? So at 50, even $display gets executed. So $display is executed at time 50. You understanding? So all the statements inside the fork join first gets executed. They have an added delay of 10 for every statement. So 10 plus 20, 30, 30 plus 10, 40, 40 plus 10, 50, and 50 is the last statement that's being executed. So then whatever is outside the statement, since $display outside the fork join has no any other delay, so 50 will be the last execution that has happened. So at 50, immediately $display, which is the outside statement, also gets executed. Okay. So in this way, fork join executes in system Verilog. So suppose now instead of join, I'll terminate the syntax with join underscore none. Then what happens? So the feature of join underscore none is all the statements execute independently. They are not dependent on each other, right? So what happens here? Inside module test, I have one process, which is initial, begin, end. And inside this process, there is one for join underscore none block, right? So then outside the fork join underscore none block, I have a statement written, okay, $display. So they all simultaneously get executed, okay? So the first statement inside the fork happens at hash 5. So which gets executed first? They all concurrently execute. So this gets executed first at the earliest because there is no delay here. So continuing immediately at 0 gets executed first. Then 5 gets executed at 5, right? Thread A at 5 gets executed. Then thread B at 10 gets executed because they all are independently executing. Okay, there is no priority here that all the statements inside the fork join should get executed first. There is no such priority because the syntax is join underscore none. So they don't wait for each other. They all start concurrently. Okay, so that's the reason you get the output as follows. So let's see one more example here. So we have join underscore none here. See join underscore none, and we have fork here. And this fork join underscore none block is inside the process initial, begin, end, right? So hash 10 is the starting delay. Only after that, the fork starts executing. But then $display happens again at 10, right? Because everything happens independently, right? So they all start after 10. So after 10, this will be the first one to execute because it has no other delay attached to it. So exit is at time t is equal to 10. And then 20 gets executed, 20 plus 10. So at 30, thread 1 will execute at 30, right? So then comes 30 plus 10, so 40, thread 3 gets executed at t is equal to 40, right? And then thread 2, which is 40 plus 10, okay? So that gets executed, okay? So it works like that, okay? So begin hash 20. So this happens 10 plus, because it's join underscore none, right? So this executes first, 10 plus 20. Then 30 plus 10, 40 gets executed. So this comment is after comment, we have thread 1 here. So this is also commented, while in the screen it's shown as it belongs to the code. No, the end, after end, we have begin again, one more begin. After end, we have one more begin. This is the these thread_1, thread_2, thread_3 belong to the comment. So they have, because of the alignment, they have just come to the next line here. Okay. So this is how they work. Now, what if I terminate join with join_any? If I add fork join with this syntax, then when I have join_any, what happens is only one of the statement executes first, and then all independently execute, right? That means the statement inside the fork join_any block, only one statement executes. Okay, and then it will not wait for the completion of other statements inside the block. It immediately goes to the statement outside the fork join_any. Okay, so how does it happen? So we have initial begin process. Inside this, we have fork join_any as one block. So A done. So after a delay of 5, A done gets displayed because this is the first statement, right? I mean, this occurs earlier, at the earliest, right? Because it's #5, less delay. So this occurs, and once one of the statement inside the fork join_any occurs, then it immediately goes to the statement outside fork join. So that is the $display. So one which is outside. So this statement gets executed. So one thread done, continuing at. So what will be the time? 5, because at 5 this happened, right? So immediately whatever statement is outside the fork block gets executed. So this is the statement which is outside the fork block. So this gets executed. Then again, remaining statements of the fork block gets executed, which is #10 in our example. So be done. So whatever is mentioned here at 10, be done is the statement that it gets executed at 10. Okay. This is how fork join_any works. For example, let's see one more example here. So we have initial, begin, end. This is the process. And inside that we have fork and join_any. Here we have #20 $display one statement, #40 $display one more statement, #30 $display third statement. Okay, and then outside the fork block we have $display again, right? So how should it work? Now #10 till #10 no process starts, but after #10 this fork starts executing. So first statement, which happens at the earliest, is the one with 20 as the time delay. So 20 plus 10 gets added and 30. So thread 1 done at t is equal to 30. That gets executed. Okay, that this is the one. And immediately it comes outside the block and executes the statement outside the block, which is this statement. So here exit is at time is t is equal to 30. That gets displayed. And then it goes back to the fork block, and whatever statements are left out after the first statement, they get executed. So 40, 30, first, next will be 30. So 30 plus 10, that means thread 3 at t is equal to 40 gets executed, then 40 plus 10. So this gets added, right? Because of the initial delay. So at 50, thread 2 done at t is equal to 50 gets executed. Okay. So this is how fork join_any execute. So now if I have a disable label in my um, program, then how does it work? So disable label, it terminates a named block only, useful to stop specific threads. For example, here I have one process, initial, begin, end here, and I have John_none here. Okay, so fork, and it's join_none. So how does it work? In join_none, all the statements execute concurrently. So they are not dependent on each other. So which one will happen at the earliest? So it's join_none. So block disabled at 5 immediately happens at #5. At #5, uh, disable named_block. So I'm disabling the block. What block? Which fork block I'm disabling? The fork block which is named as named_block. This one. So disable named_block. So this block gets disabled at 5. So then at 10, this had to have executed, but it will not because I've disabled this block at 5. So at 10, whatever is there will not get executed because it's already disabled. Okay. So $display block disabled at 5, and that's it. It comes out of the code. the entire code, it comes out because we have disabled the block. Okay. Suppose we had disabled it at hash 20. At hash 20, what would have happened? Then this was waiting, right? So by then it will go to this block and hash 10, this will get displayed. Okay. But then after this getting displayed, it will come here and later it disables the block. So by then this would have been displayed. Okay. So it depends on how you disable, at what time you disable the block. Based on that, uh, either this entire block gets displayed or it will not get displayed. I mean, it will not get executed. Okay, so that's how it works. Then we have disable fork, similar to disable, the entire block being disabled, uh, based on which block we are disabling. We can also say disable fork. What does it do? So when I say disable fork in my code, then it terminates all child threads under current fork. May stop more than expected. So like this, here I have module test, initial begin, fork, join underscore none is the block wherein I have two statements inside the fork block. One which is at 5, I'm displaying A. One which is at 10, I'm displaying B. Okay, but it's inside join underscore none. So at 6, we are saying disable fork. At 6, we are disabling it. So before that, this executes. Correct. So at 5, display A gets executed. So A gets displayed, right? But then immediately at 6, this all are happening concurrently, right? So at 6, this executes, okay, and it disables the fork. When the fork gets disabled, after 5, after 6, whatever statements are there, they don't get executed, okay? So A, then all fork threads are killed at 6, that's all. So this will not get displayed because it's after 6, right? So only this statement and this statement gets displayed. Okay, so that is how disable fork works. Now, suppose I say wait fork in my program. So here I have a process, initial begin, and fork join underscore none is the block which I have written. Then at 5, we call the display command, display function. It's a system task which displays T1, which is just a message, and one more display which displays T2, again a message. So these are at 5 and 10 respectively. But then I'm saying wait fork. So though I have join underscore none here, and it actually, how does a fork with join underscore none work? All the statements work concurrently. But now in this case, I have mentioned in my code wait fork. So all the statements outside the fork execute only after waiting for the fork. Okay, so fork should happen and then only the other statements execute. Okay, it's very much like fork join. Okay, equivalent to fork join here. Okay, so begin hash 5. So hash 5 command, whatever is at hash 5, that gets executed. That is T1. Whatever is hash 10, that gets executed. That is T2. And fork is done now. So waiting is done. Then the statement next to that, which is $display, gets executed. All threads finished at 10. So that's about wait fork. Okay. So now, system Verilog mailbox, we have system Verilog mailbox. So what is that? So it's mailbox is used to communicate between threads. Okay, so that is mailbox. So it is a system Verilog built-in synchronization and communication mechanism, which is used to pass messages or objects between parallel threads or processes. So it behaves like a FIFO queue. Okay, so what are the key features of mailboxes? It's like a FIFO structure, no predefined size limit, automatic, it's an atomic operations. It has atomic operations like put and get are safe from race conditions, and it can suspend a process if mailbox is empty. So it can suspend the process in blocking it. Mailboxes can be typed. For example, you can just have, you can have in the mailbox, see mailbox hash of transaction. So what does it mean? That mailbox is carrying a data of type transaction, wherein transaction may be of type class. Or I can have untyped mailbox. Example, I simply say mailbox MB. Now, when I say this and when I instantiate this, like MB is equal to new, now this mailbox with the name MB can put a data which can be of any type, integer type or a string type or a class type. Okay, so we are making it a generalized one. But if you make it a typed one, like I have said hash of transaction, then it becomes fixed. It only puts the data or gets the data of type transaction and nothing else. Okay, so it's not generalized now. Okay, so a mailbox can hence be typed or untyped in nature. So what's the use case of mailbox? They're ideal for communication between driver and monitor. That is one thing. Or I'm just uh, decreasing the screen size so that you can see the text here. Or you can use it for synchronizing across parallel threads. Okay, so basic mailbox syntax. What are the different mailbox syntax one can use? One is if you want to create a mailbox, you have to use a new operator. So that creates the mailbox object. Okay, but before that, mailbox can either be typed mailbox or untyped mailbox, as I said. So here we have. I'll just take the pen here. Here we have hash transaction, which is typed mailbox. That means this mailbox can put or get data of type transaction. And this transaction can be representing a class object. Okay. Then the other syntax of mailbox are if I want to write data into the mailbox, I use the command dot put. Okay, so this is the object name of the mailbox, mbx dot put off, and whatever you want to put into the mailbox. So here I have put object of class transaction. So trans underscore h. So this is an object of class transaction. Okay, and it's blocking in nature. Okay, so it blocks. If it's full, it blocks. It just waits until there is a space to add data. Okay, and mbx.get is something which gets transaction from mailbox. So it's also blocking. So if the mailbox is empty, it keeps waiting until the data is available. Okay. We also have non-blocking get, which is of the form mbx.try underscore get. So this returns true or false based on the data availability. Okay, so if data is there, it returns true. If it's not there, it returns false. So it's a non-blocking. It doesn't wait and hang the program until the data is available. Okay, so we also have the mbx.peak, which is peaking without removing the data, and mbx.try underscore peak, which is non-blocking peak. So like blocking peak, we have non-blocking peak also. And if I just want to know how many data are available in the mailbox, I can just use the command mbx.num, which tells me number of items present in the mailbox, and that is returned to a variable. You can store it. For example, here I'm storing the number of items in the mailbox in a variable called as count. So that is how these are the different syntax of mailbox. So for example, here I have a mailbox mbx, and I've mentioned it of, it's a typed mailbox. I'm just telling that this object mbx, which is of type mailbox, deals with integer variable. So hash of int, and I've instantiated the mailbox mbx. Then inside the fork process, initial and end in the process, what we have done is we have just taken, after a delay of 10, we put a data, mbx.put of 42. We are putting a data of 42 there. Okay. So again, we have one more process. So begin and we have two process here. This is one process and this is one process. So this process is writing into the mbx, writing into the mailbox. So in this fork is not there, it's a type error. Writing into the mailbox. Okay, and so 42 is written. And now this is another process which is reading from the mailbox. So it's mbx.get. Okay, so what happens here? Okay, sorry, here there are two parallel processes, so we need fork join. right? Because it's parallelly happening. So fork join is required for concurrent process. So inside fork join, we have two blocks. One process is writing and one more process is trying to read. Okay, so that's the reason we need this. So initial and inside initial, we need to have fork. Okay. So what happens here? In this process, we have a variable val. So what are we trying to do is we are reading that mailbox data into val. Okay, that means val will get 42 now. So when I say puts of value, um, I'm just displaying the value here. So dollar display received 42. So that will be the val will have, so val will have the value 42, which is received in the variable val. So we'll block until producer puts value. So this is entire thing is actually the comment. Okay, so this is the comment. So mbx dot get of val is the syntax. So val will have 42 and that gets displayed here. Okay, so initial, next line we should have fork, or you can keep it here in the same line. And then we have begin, end, and then join. Okay, so that's how this works. Then, so received 42 will be the output. For example, here I have two process. We have class generator and we have class driver. So we are trying to communicate between the two. Generator and driver are communicating with each other. So mailbox is typed mailbox, which is of type hash trans. So it belongs to the class trans, and the object of class trans is trans underscore h. And we are creating a mailbox by name gen to drv, right? That's the generator to driver. We are writing something. So we have function new, which is getting gen to drv variable. And then I'm assigning uh, whatever I get gen to driver, whatever I'm getting, I'm assigning it to this dot gen to drv. So end function. So that's the new function which I have written. Otherwise, we just call it as new. But here, since we have one variable to pass, we are separately writing function new. Okay. Then a task is written. So wherein I have inside the task start fork join underscore none block. Okay. So wherein 10 repeat of 10. So 10 types, I'm repeating a process 10 times. So repeat of 10 begin. What am I doing here? Object is created. 10 different objects of type trans is created. So tran underscore h is equal to new. And I'm asserting assert of tran underscore h dot randomize is done. So whichever variables are of type rand or randc in the class trans, they get randomized, and assert will send um, a syntax failure message if randomize is not happening successfully. Else the data will have a random value. All the variables which are rand or randc will have random value. And then I'm putting that data, whichever is generated, I'm putting that data into the mailbox. So gen to drv dot put off. So mailbox, what is the name of the mailbox? Let me explain. So gen to drv is the mailbox. Okay. So there I'm putting trans underscore h data. It's of type, it's not int now, but it's trans underscore h data. It is trans. Okay, that's been put here. Okay, and how many such data we are putting? Such 10 data, 10 trans underscore h random values are being put. Okay, now this is done by the generator. So it's generating data. Now, what will class driver do? Class driver has to read this, all the 10 datas which the mailbox is having. Okay, so which are again of type gen to drv. So it has to read from the same mailbox. So I have initialized the same mailbox object here, which is gen to drv. And then this dot gen to drv equal to gen to drv, we are assigning that. Okay, that's the function new. And we also have a task start here. Okay, so repeat of 10 times gen to drv dot get happens here. So driver will generator will put the message, driver will get the message. Okay. Now I'm synchronizing the receiving of message by using what is called as the clocking block. Okay, so at passage of duv if.cb.enable, this is nothing but it relates to a clocking block which is inside the interface. Okay, so the entire program is not shown here. We are just putting the data onto the mailbox with the help of generator. So generator puts the data, and with the help of driver, we are reading the data. Okay, so this does put and this that's thus get. And synchronization of data is happening through clocking block. Now, clocking block is something which is written inside the interface module. Okay, and that gets initialized or instantiated inside the test bench. Okay, so we have join underscore none here because everything should happen parallelly. No process is dependent on each other. Okay, so flow summary, env creates a shared mailbox. Now this mailbox is shared. What is the name of the mailbox? Gen to drv. Generator creates randomized transactions and sends them via put. Driver fetches transactions using get and drives them after a signal or event. Okay. Fork join underscore none ensures that the loop doesn't block the thread. So they all happen parallelly without blocking each other. So this is a little involved code which I have shown here. So you can just execute this by completing the entire program. So you need to write the DUT, and you also need to write the interface module. And inside the interface module, you have to also write the clocking block because we have used clocking block here to synchronize the things here. Okay, everything to be in sync. We are in need of synchronization to be done here. So we have used clocking block here. Okay, so if you combine this entire program and execute, you'll get a better idea about what's happening here between a generator and the driver. So, we understood threads, we also have what are called as events in System Verilog. So, they're used for communication and synchronization purpose again. So, the syntax for that is starts with the keyword event and the name of the event. So, here example, we have mentioned EV as the event name. And how to trigger that event, you have to use this symbol. Minus followed with greater than, so it's an arrow like symbol. So this triggers the event or activates the event, and until the event is triggered, if another process has to wait for that event, then at is the command, at of event. So this waits for the event to be triggered future only. So if this event has happened in the past, it will not understand, it will not recognize it. So it will understand only if the event is triggered in the future. So at of EV. Suppose you want to consider the events which have happened in the past also, then you can use wait of EV dot triggered. Okay, so wait for event even if triggered earlier in this timestamp, it can recognize whether an event has occurred in the past. So you use wait for that. Okay, and how do you generate an event? You can just say new of EV. Driver is new of EV, so that you can pass event into a process like this. Okay, so driver is new of EV. Pass event into classes or methods. So this is an example of how you can pass EV into a class or a method. Okay, so let's see an example. So I have done as an event. Okay, the name of the event is done. So inside the initial begin process, after a delay of 10, I'm triggering the event done. So this is triggered. Okay, so this is one block which is triggering the event, and I have one more parallel block which is waiting for the event to be triggered. Okay, so at done. So when this event gets triggered, it is recognized here by this block. Okay, so at done, it will understand, and then it goes to the statement saying event received at time. So when it received the event at 10, right? So at 10 this got triggered. So same time this recognizes that trigger, and this display command gets executed. So event received at time 10. Okay, so one more example here we have. So initial begin $display about to drive seat control after 10 time units, hash 10. So till hash 10, no event is triggered. So $display control is driven at time. So about to drive after 10. Okay. So this gets displayed first. Then control is driven at time t is equal to 10 gets displayed, right? Also this first this gets displayed, then second this gets displayed because they are not with any delay. These two are parallel process. This is one process, this is one process. So parallelly they are happening. So this gets displayed first, then this gets displayed next. Then after a delay of 10, uh, this is waiting at EV, so it's not a triggered. So here after a delay of 10, this gets triggered. Dollar display control is driven at time t equal to 10. So it triggers, but then this cannot acknowledge it because act of EV is after 10. After 10, this gets executed. So by then, this has already been triggered. At 10, it's already been triggered. Okay. And after 10 this gets triggered, so it cannot, because this has happened in the past, right? So it will not get to know that, so this statement doesn't get executed at all. Suppose this delay was not there. If this delay was not there in this process, in the second process, then after 10 when this was triggered, it would have immediately acknowledged it and this statement was getting displayed. But here we have this hash 10 statement. Only after that this wait gets triggered. So this has already happened before 10. That is at 10 it has happened, and this will not this cannot understand the occurrence of that trigger because it has got activated after 10. So this data will not get displayed. The statement will not get displayed. Okay. If you had not included this, then of course it would have recognized it. Okay. So either you have to remove hash 10 so that this acknowledges the trigger and displays the statement, or you have to use, as I said, you have to use what is called as, here I have removed it. I've removed it here. Hash 10 is not there. So this data is driven after control gets displayed. Or you have to use wait of, as I said, wait of EV dot trigger. Now this will acknowledge the events which have occurred in the past. Correct? So I can use this, or I can remove this and just say at of EV. Okay, anything is fine. So then all the statements get displayed. So that's about the events. Next, we have semaphores. So semaphores, they ensure mutual exclusion. The purpose of semaphore is to ensure mutual exclusion. Only limited access to shared resources. Whenever we have limited access to shared resources, we take the help of semaphore. For example, I have a bus, a memory, which is used by multiple processes. I have only one single resource of memory or one single bus, and multiple processes need to access them. Then we need to take the help of semaphore so that there'll be no conflict when that resource is being accessed. Okay. And hence semaphore is used to synchronize parallel processes like fork join blocks or multiple threads. The features of semaphores are multiple keys can be put into or taken out of the semaphore. Access to shared resources is controlled by availability of keys. Think of it as a bucket of tokens. You can only proceed if you get a token. Okay, that's how it works. For example, here I have semaphore sem, that is the syntax. The keyword is semaphore, and the name you can give any name. Here I've given the name as sem. Then I'll have to say sem is equal to new of optional initial key count. You can name it, or you can just say new of 0 or new of 1, indicating how many keys you're creating to that semaphore. Okay. So when I say key count is 0, optional initially you're giving a value of 0 to it. Okay. Then I will say block until keys are available. Okay. So sem dot get optional num keys is 1. I'm saying 1 now. Okay. So sem dot get, I'm taking a key now. So what is the value of that key? It's 1. Okay. Then if you want to release the key, you have to just say sem dot put and tell the number of the key, whichever key number you have generated. You're releasing that. Okay. So if it's 1, when you say sem dot put, that same key will be released. Okay. So how it works, sem is new of 1. What does it do? Creates a semaphore with one key. With one key you're creating. Okay. Sem dot get of 1. What does it mean? Blocks the process until one key is available. Once acquired, it reduces the key count. Okay, so when I say when a code has sem dot get of 1, it keeps waiting until it gets the key. Okay, so and once acquired, it reduces the key count. Okay, then sem dot put of 1 releases one key back into the pool. That is how it works. Let's see with an example. Here we have sem equal to new of 1. So one key I have generated, and maybe it's for mutual exclusion. Let's see. Then we have a process now, a block fork join, and inside which we have two process, begin, end, and one more process, begin, end. So they have to happen concurrently now, right? So here, dollar display, only one key is there, mind you. So dollar display thread one waiting for resource, sem dot get of one. So thread one waiting for resource, thread one got resource, dollar display. As soon as sem dot get happens, and if the key is available, thread one got resource, right? And after a delay of 10, sem dot put of 1 happens. But here, see, in the second process, in the second block, concurrent block, hash 1, at after a delay of 1, thread 2 waiting for resource, right? It's waiting. And sem dot get, it wants the key now, but it will not get it until 10. See, until 10, because this already has taken. Any one process would have taken the key, right? So then the second process will not get it until this releases it, until a put happens, right? So here get happened, thread 1 got the resource, and this is still waiting at hash 1, it's still waiting. And when sem dot put of 1 happens after a delay of 10, this will get the key. Thread 2 got resource. Released resource, thread 2 got resource. Then after a delay of 10, it puts the key back. Which one? The thread 2. It puts the key back. Thread 2 release the source. Now, the other process, if somebody is waiting, can get. Okay, so this is how it works. Let's see one more example here. So we have module automatic test. So I have used automatic here. So that's the module name. We have a driver, it's a class, right? And two instances of, two objects of driver class has been created, dr of 1 down to 0. Two objects have been created. Semaphore semaphore for resource control. Now see, we have a block here inside initial begin. What's happening here is for each dr of I, that means dr of 0, dr of 1, we have two, right? So dr of 0, dr of 1, we instantiate the constructor is instantiated. Dr of 0 is new, dr of 1 is new. That happens. Then sem is new of 1. So when we said sem is new of 1, only one key is generated for the semaphore, which is for mutual exclusion actually. So then we are having fork join here. Inside fork join, we are calling a dr of 0 dot send. So it calls the task. Dr of 1 dot send. So even that calls a task. So one of the driver gets the key now, right? So in the task send, see, so we have dr of 0 dot send, dr of 1 dot send. So this is the class driver. So it has task inside it. So that will be called. So this will be called. So task send sem dot get. So one of the driver gets the key, and we have a clocking block here. So the values get assigned to the objects variables based on the clocking block synchronization details. And once it assigns the data to the variables, it releases the key. And then driver 2 gets the key, and the same process happens. Okay, so how does it work? Two driver objects are created. Both attempt to execute send concurrently using fork. Inside send, the sem.get1 ensures only one driver accesses the shared bus at a time. After using the bus, sem.put of 1 releases the key, allowing the other driver to proceed. Okay, so only one driver first accesses the bus. So, and then to the bus, you assign these values. And once it releases the key, only then the other driver gets access to the bus. Okay, so that is how the semaphore comes to our help. okay, in order to avoid conflict when only one bus is available and two processes are trying to access the bus. Okay. So for example, here, one more example we have, wherein semaphore sem is the name of the semaphore. We have created three keys for this semaphore. So, but the processes which are trying to use the keys are five in number now. So only three will get the key in the beginning, and whoever releases the key first, uh, fourth or fifth can make use of that. Okay. So task use buffer dollar display. So waiting for the buffer. Then sem dot get of one request one buffer dollar display. So waiting for buffer. All are waiting for buffer. Then P1 got the buffer, right? Then P2 got buffer, P3 got buffer. So all the three keys are now exhausted. Okay. Now whichever releases, P1 released the buffer. Once P1 releases buffer, P4 will get the buffer. P2 releasing buffer. Then P5 will get the buffer then. Okay. When P3 releases, P4 releases, P5 releases. This is how it works. Okay. So at once, only three processes can get the key, and then the other two processes have to wait. And whichever releases the key, they take it from that process. They take the key based on that. Okay. So, so that is how this parallel concurrent execution works. Okay, the summary is threads for parallel execution. System Verilog uses concurrent threads using fork join underscore none, or fork join underscore any, right? So three variants we have under fork. Which are all used for parallel tasks like running multiple drivers, monitors, or test processes. Okay. Then we have mailbox, and mailbox is used for communication between threads. A built-in parameterized class FIFO-like structure it is. And it has blocking methods as well as non-blocking methods. So blocking methods are get, put, and peek, while non-blocking methods are try underscore get, try underscore put, and try underscore peek. Okay, used case are transaction between producer and driver. And then we have semaphore, which are used for mutual exclusion and synchronization. It's a built-in class used to limit concurrent access to a shared resource. So how does it control many processes to enter in many processes to access a resource? It is via keys. Okay. So use case sharing a single bus memory or limited hardware resources among threads. So events we have understood for thread synchronization. The different methods are to trigger the event, it's arrow, that's minus followed with greater symbol. To wait for an event, it's at of EV, which will not consider the events which have triggered in the past. They only consider the events which are occurring in the future. So if you want to consider the events occurring in the past also, then we have to use wait of EV dot triggered. Used case is signal when one process has completed or reached a state, so another one can proceed. Okay, so um, that's the reason we want events for. Okay, so that's about these different mechanisms of concurrency and synchronization in System Verilog. Thank you very much.